So, hello everybody. My name is David Beard. I'm the developer evangelist for the Vuforia platform. And I'm going to be showing you a new feature of Vuforia that enables the reconstruction and tracking of surfaces and objects in your immediate environment. This is called Smart Terrain. And it provides depth awareness for today's devices that are using a standard smartphone camera. It is employing advanced reconstruction techniques to generate a 3D map of your environment, of the surfaces of your environment and also objects in your environment. And interestingly, it provides these as distinct meshes within the Unity environment. We're offering this immediately for Unity. So you'll be able to create smart terrain applications using Unity and really just authoring them as a Unity scene. So smart terrain is capable of detecting objects, it's capable of detecting surfaces, and it's actually capable of understanding and synthesizing edges on the surface area. So what that provides is it's enabling apps to have an awareness of the physical environment, the physical context of the user, and to actually then impose or to utilize the physical properties of that space, which is the dimensions of the objects, the distance to things, the proximity of things to each other, and the general area that the user is constructing for the smart terrain experience. So really the application, the use cases that we're thinking of immediately are that smart terrain can be used for developing new types of games. That you can create a play space with that. You can create a new game level or a game court of some sort. You can actually create meshes using smart terrain for a game space and then persist those and take them into another gaming application. So you can share spaces potentially. And it's also good for the range of like product visualization applications, in-store retail applications, and other technical applications where you want someone to be able to actually construct an augmentable environment within their context. So I'm going to show you how to build and customize a smart terrain application, and also address some critical points around the design of smart terrain applications, the user experience that you want to try to induce, and behaviors that you want to inspire in the user, the type of feedback that you want to give them, and then how to manage the life cycle of the application and the types of events that you're going to be responding to in order to provide an effective smart terrain experience and also get good performance out of the smart terrain engine. So before we get into that, we've developed, that's not going to stop for me. Hold on one sec. There we go. We've developed a best practices application. We're going to be distributing this very soon. And so all of what I'm showing you here and all of the practices are actually going to be provided as part of a sample application with the Vuforia SDK, and that's coming out soon. But what I'm going to show you is really what range of practices we recommend for getting the best smart terrain experience for the user and for getting the best performance out of your smart terrain application. And so what we're really trying to highlight with this it's not a prescriptive way of developing smart terrain apps, but it's really recommendations that we've found in our own research and experimentation with smart terrain that are going to enable a naive user, somebody who's never worked with this technology before, doesn't know a lot about AR, doesn't know about reconstruction techniques, how to enable them to get the sort of experience that you're trying to provide with your application. So what you see here is as a simple principle, we're providing a visual guide on screen. And what this is indicating to the user is that they should match up this can outline with the can shape. And here's an example of the target that's part of the application. What this does is it gets the user right up on the target, and it enables them to initialize the experience effectively, right? So what it's giving them is an intent. It's saying, look, the first thing you need to do is capture this target, and then once that's recognized, you can proceed with the experience. And what you'll see is we're giving visual feedback to the user indicating, okay, it's been recognized. Then we start updating the surface reconstruction, which is the blue ice, and we're also doing object reconstruction. So here we're showing an approximation of the object shape. You may or may not reveal that to the user. But what it's demonstrating is that after the target's been initialized, you're providing feedback telling them to pull back, capture the scene, and then what's being executed is the reconstruction of the surface as an icy surface in this case, and also the recognition and reconstruction of objects on that surface. So when we talk about this, we talk about really the development of smart terrain applications is a three-phase execution. There's a staging phase, and that's actually performed by the user. There's a scanning phase where the user is capturing the scene, and there are events when that's occurring that are being returned by the SDK that the developer is providing app logic to respond to. And that's how you're really customizing the behavior of a smart terrain application. So once they've gone through scanning, You can give the user a choice, or you can use app logic to determine that, okay, the scanning phase has been culminated, and now we're going to actually start rendering content, and they'll go into a play phase. And this is when they're going to execute really what the subject matter or the intent of the application. Are they playing a game? Are they visualizing something? What are they doing with this? So let me talk about the supported environments for smart terrain. Smart terrain is really best recognized as being a near-field experience. And what that means is that it's in the range of myself to the table, maybe television viewing ranges, so near to midfield. And you're really talking about, what would you say, an intentionally crafted space. So it works very well with an area that starts off really as a flat reference plane and provides a visually distinct area. What we'd like to talk about is it's very good for things like indoor tabletop experiences or against a floor area that's visually distinct from its surroundings. It's good to provide a boundary because smart terrain is going to be looking for edges. And when you're generating that mesh, it's good for, as a development, what would you say, consideration, to understand the general area that you're going to be working in, that it isn't extending off indefinitely and that it has sort of a regular geometry so that you can execute apps within that. So really, I guess the principal considerations is, again, visually distinct, flat surfaces. This, because we're working really with a monocular camera in this case, it's useful to really provide a flat reference plane as what you might call the primary reference or the primary surface, as we call it. And what this means is that the other objects on the surface are really understood in reference to that primary surface, right? So that's providing, but if you thought of it as a hierarchy, it's really providing the primary reference for the development of the scene, right? And so you're going to stage the area, stage the flat area with the range of objects that are supported. Really, what we're looking for here in picking up an object is it needs to have a pattern on it of some sort. And what we look for is typically the pattern of contrast variation. So you're looking for detailed patterns. You don't want to use something that's clear. This wouldn't necessarily work well. Things that are reflective. What you need is for the features of the object to be visually consistent as you're moving around them. If they're changing because of reflection or changing because of transparency, they're difficult to, what would you say, isolate within the field of view of the camera. And also, in selecting surface areas, you don't want to use something that has what appear to be internal borders. And this is things like you don't want to use tiles. Floor tiles wouldn't necessarily work well because what's happening is, let's say I put the target here and we have tile borders around it. What it's going to, the tracker is going to assume is that, oh, this is just actually a very small area and it's being bordered by edges, right? So the critical thing, if you've worked in AR before, developed in this area, is that really the camera can only see the apparent details of the image that it's capturing. It isn't, unless you're using something like IR or another technique, anything that's optical is really seeing the same thing that you're seeing. So when you are trying to understand what am I looking at as an environment that I can use, it's really, and this is something that can be communicated to the user, it's really what they're capable of seeing and what they're capable of understanding as being distinct from their surroundings. And that's how they can identify what is useful, really, for the purpose of developing a smart terrain app. So I'll talk about the correspondence of real to virtual artifacts. And so from the development perspective, what you have is that the user is going in, they're staging a setting where they're going to be executing this application, and that's then returning a digital artifact through the SDK to you that you're responding to. So typically you're going to be handling this through an event handling technique. But the principal one is when I talked about this surface area is that the stage corresponds to the primary surface. And so if I'm using this tabletop and that's my stage area, when I reconstruct that, that is being returned as the primary reference plane, as the primary surface of my application. You can think of it as like the ground plane of your world or the ground plane of your scene. So what you can do with this also is just as a sort of development tip, is they've selected their area. It's a good idea just due to the performance considerations of smart terrain, which it's computationally intensive to generate these, to reconstruct surfaces, track them in real time, to reconstruct props, track them in real time. So it's a good idea to have app logic that actually delimits how far you can go with that. We provide a mechanism internally that you can set a maximum area. You can also use techniques that are actually calculating the accumulated area of the meshes that you're creating. So it's just, as a tip, it's a good idea to be aware of how much you're trying to track in real time. So As far as the constituent artifacts, we have the primary surface, we have the stage surface. Now, smart terrain is initialized by what we refer to as an initialization target. This is a predefined target that you would create through our target management platform. And what this gives you is a ground truth reference. You're going to, you know the size of this. So you can provide that as a reference to the smart terrain application. And what that enables you to do is then infer the real scale of the scene that you're generating, which means that you can work with real measurements of size, scale, and distance from things, which makes it interesting. When you're actually augmenting a real-world setting, you then have a sense of how large or how expansive the area is and where these things are in relation to each other. So when you talk about, or when I talk about the real to virtual correspondence, that's what enables you to develop a virtual scene that actually matches accurately as a dimensional or physical characteristic into the virtual environment. So the initialization target also, just as a sort of principal application of it, is it's giving you the scale reference and it's also telling you where your primary surface is. So what you're doing is when the scene is being reconstructed, the first thing that happens is that your application recognizes this, initializes the tracker to update the mesh. And so what that's doing then is it knows, okay, the bottom of the can is here, therefore the primary surface should correspond to that, and it gives you a much tighter registration of that surface generation in relation to the target that you're using. So you have known targets, you have a stage that they exist on, and then we have a notion of props. And really, props are simply unknown objects. They haven't been defined, and they're a prop for the fact that you can really do what you want with them. You can have them take on varying significances depending on what kind of application you use. So if this is a prop that I choose to use, the milk bones, I may turn this into a castle, I may turn it into a mountaintop, I could turn it into a toaster if I chose to. So really, being that this is not known by the SDK, it's being reconstructed as runtime, I can take it and really change it as I want to after it's been reconstructed. So we recommend really keeping it at about 5 props just as a performance consideration. But the interesting thing about the assignment of props is that even though they're not known at runtime, they're not predefined, is that when they come in, when they're reconstructed, you're getting a mesh of this, which means that you can determine its size, you can determine its distance to things, you can determine, how close it is to the initial target, how far away, how big it is. So you can actually customize the application based on the physical properties of the prop that you're bringing in, which enables you to a lot of flexibility in how you actually treat the prop objects that are being brought in. So now I'm going to talk about how to address the life cycle and states of a smart terrain application. So one of the interesting considerations here as far as the customization of a smart terrain app is, unlike a lot of other types of applications, your user is actually creating the, what would you say, world environment that the application, the scene is existing in. So you can incorporate an inventory of props and you can incorporate app logic, but they're really the ones that are going to be determining how the scene is crafted in the real world. And as I go through this, I'm going to keep on coming back to the idea of user experience and feedback because it really is significant to both the performance of the app, but also the success of the experience that you're trying to develop for. So again, the first action within the runtime execution of a smart terrain experience is really that the user is recognizing and initializing targets. So this has been predefined. We know the scale. When that's been recognized, there's a method that's called internally that's start mesh updates. And basically all this does is tell the tracker that, okay, we recognize this, we know the scale, we're now going to start reconstructing the scene. And within Unity, you can do this as part of the authoring workflow. There's simply a checkbox that you can use to initialize it. Or if you want to customize the app further, you can actually call that API method specifically to control the life cycle of the app. And so what you'll see is that when you're integrating smart terrain to something, we provide you full control over the life cycle of the tracker for the purpose of creating the scene, which means that you have control over when it starts to update, when it stops, you can reset it. And so it's not like a black box. You have an ability. We work really within, or what we offer as an authoring workflow is really the primary way of creating these applications. But we also provide full API level access. So our authoring workflow is sort of addresses the 80% of use cases that most people are going to need to use to customize an application for smart terrain. But then also you can get a little closer to the metal and go in and work at the API level if you choose to. So again, once it's initialized, mesh updating starts. This is, again, recreating the surface. It's looking for a flat surface. It's going to start capturing any feature that it can to start expanding out the map within the constraints that you've defined. And as that's occurring, there's a callback that's being triggered, which is onSurface updated. Now, the interesting thing about onSurface updated is this is giving you a surface behavior which is really keeping track of the state of the surface object, right? How, what is it updating? What's its activity? Is it enabled? Blah, blah, blah. But it also gives you access to the mesh that's being created. And this is a valid 3D mesh. It's a triangulated mesh. It's coming out of the Unity engine. And what you can do once you have that is start again looking at physical properties of the mesh. You can understand how big it is, where is it going in relation to the initialization target, how is it expanding, in what direction. And also you can start immediately providing rendering techniques. The nice thing about the fact that we're really providing you a valid 3D mesh is that you have all of the features that are available to 3D meshes. You can apply physics to them, you can apply rendering techniques to them. And this is all within the Unity environment. This is just treated as a standard mesh. There's nothing special about it from Unity's perspective. We're just returning it to the Unity engine effectively. And so this is what the user may see within this. And again, in talking about the user experience and trying to induce good behavior from users, effective behavior from users, it's good to give them some feedback. And so within our sample app, you'll notice that we have a little piece of ice that comes up. There's an iceberg that comes up around the can, just to tell them, look, your target's been detected. Now, as the surface is being generated, we're showing that, look, you're effectively scanning the surface. There's something happening. You're doing something right. So what we're indicating to them is pull back, capture everything within the field of view of the camera, and you'll see that this area begins to expand. So as they're doing that, they'll start bringing props into view. And so what you're seeing here is really that you have the surface expansion, and then independent of the surface, you have the recognition of the fact that there's an object on the surface. So again, one of the nice features of Smart Terrain is that it's not that we're just giving you a topographical release of the surface contour that isn't distinguishing really the contents of the scene. We're actually recognizing that, look, again, initialization target, surface plane, and objects on the surface. So you can respond to all of those within the application. Now, when it does detect an object, there's another callback that's created, which is onProp created. And what this does is it provides you with really a reference to the mesh that is approximating the size of the object that you brought in. And you can then associate that with a prop template. And the prop template is really a prop behavior that is undefined. When you add a prop to it, it becomes concrete. And now you have an object instance in your scene that you can track in order to understand what the position of the prop is. And I think one thing also to sort of call out here is, again, when we talk about environments and supported environments and the considerations, once these things are placed, they need to remain stable. Really, you're looking at, when you talk about the staging phase, it's the understanding that, look, you have an area that's visually distinct. You need stable lighting. You need consistent, stable lighting over that. And again, this gets to what are the apparent features of the scene? What can the camera actually respond to? So we need consistency there. We also need consistency in the placement of the prop. So once it's been recognized, it needs to remain where it is. At this point, we're not supporting moving props around after the terrain has been generated, which is just something to be mindful of. So really, again, once you started updating, the principal role of the developer here is really to customize the handling of updates. And again, that's as the surface is being created, as props are being created. And there's also two other callbacks that occur, which is that when a prop is updated, meaning that a prop, really the reconstruction is an approximation of the size of the prop. And you'll notice that we're using bounding boxes for that. So it isn't a smooth contour. It's not that we're doing like a 3D capture of the surface of it and trying to do that with a single camera. So really what it's going to give you is what are the bounding dimensions of that. And you'll notice that when you're running the app, it'll iteratively improve the registration of the bounding box, basically. So you'll see it move around a little bit at first. This is the design consideration as to how much of that you want to expose to the user. But internally, because of these updates, you can actually measure, let's say, the statistical difference in the dimension to understand when it's stabilized. And it gives you that ability to determine from the user experience perspective how much, when you want to reveal the prop is rendered, how you want to handle the prop, da-da-da. And also, we have an onProp deleted callback. And what this is telling you is that you may have instances because, let's say you have two things that are close to each other, like that it sees them as being a single object, because from the perspective of the camera, this appears to just be an extension of this. But then as you rotate, you realize that they're actually apart from each other. What onProp updated or deleted will tell you is it'll kill that first object and actually return two independent objects for that. So again, it's part of the process of the fact that the tracker is capable of refining its approximation of prop placement in the scene. And then what you're doing really in developing all this is determining when you actually want to stop the updating process. So there's really two options here. You can provide this as an interactive step to the user, which is to say, okay, have I covered your scene? Do I have the objects you need? Go ahead now and I'll stop updating, right? And again, we give you access to the life cycle to do that. And also, you could do it using app logic, which is to say, okay, you found 5 props, or you've accomplished a certain surface area, so we're just going to stop it automatically, knowing that for a certain performance consideration, we don't want the impact of continuously expanding these reconstructions, basically. So just to recap, from the development perspective, what we've got here is the life cycle is that you're starting a mesh update. When the surface is updated, you're receiving a surface behavior back, which it provides you access to that mesh, right, to the surface mesh that's being created. When a prop is created, you're provided a reference to that reconstruction. You can associate that based on whatever custom characteristic you want to apply within app logic. As the prop is updated, you're continually receiving an update on that mesh, so you can understand how it's changing. And then when it's deleted, you're acknowledged that it's actually deleted, so you can replace the prop reference. And then once the user or your logical constraint has determined that the scene has been completed, that you have the full stage captured, you call stop mesh updates. So you can see it's a very, very simple programming model for getting into this, and it's largely event-driven. So if we could turn up the lights a little bit, I'll actually run, or try to run. It's going to take me a second to set up. Just one sec. You guys got to break into my phone now. So as far as the consideration for the props, what we tend to recommend is the range of, sort of soup cans to large cereal boxes. It's good for objects that you're going to be able to fully capture within the field of view with the camera. That's one of the critical things to understand, is that you want to be able to get the entire geometry of the object in there. So as I come in, what I'm doing here, you can see that it's recognizing the can, and see those white boxes? They're actually showing the approximate reconstruction of the object. So what I can do, I pull out, and then as I move around, you'll see that the approximation improves somewhat. I'm trying to get that one. So that's pretty good, right? Now, I can click Done. And what we're doing is this is going into the rendering phase. And you can see I'm able to apply shaders to all of these. These are sort of deliberately outside of the scale of the box. You can see they're a regular shape, so we didn't just render onto the box surface. And then what we have here is that you can see that by default, we're providing colliders on all of these. When the objects are returned in Unity, they have default sort of physics characteristics, and you can obviously customize them. But we're giving them like bounding boxes. Come on, little guy. I think he's stuck on the ice. So there's a little collider on the penguin that we're playing with. But as you can see, he's able to understand where the perimeter of the objects is, essentially, and skate around on the ice. I'm trying to find a path through that. One of the interesting things is that you can also, can you see that? Try to get it to focus. Sometimes you can trigger it. There you go. But there's a technique also you can apply nav meshes to these. So you can take the mesh, and we support A*. So if you, this is using a simple controller logic, but you can actually apply nav mesh logic to this if you want to. So let me take you into the Unity context and show you how all of this is set up. Hold on 1 second, it's going to throw an error. Now, I said we had a few Unity devs here. Let me just take you quickly, for people who aren't familiar with Unity, into this environment so that you can understand what you're looking at here. So Unity is a game development engine, and you primarily develop Unity apps using, at least in our sense, using an authoring workflow. And what that means is it's using drag and drop. You're using visual design and development techniques within that, and you're really customizing the scene by adding script components and such. So as an example, when you look at, how is that on the screen? Thanks. When you look at this object in the scene, you'll notice that all of its properties are defined over here on the right-hand side. This is called the inspector. And this is really giving you the ability to configure the properties of that object, and also to provide settings and to provide modes to it, things like that. So this is all done as drag and drop, clicking, selecting. You know, it's like it's a GUI interface, basically. So let me I'll build the Penguin app for you, and you'll see how quickly we can do this. I'm going to create a new scene. Oh, let me just back up quickly. This is the inspector. This is your scene view. This is these are your project contents right here, right? And then this is the hierarchy in the scene. This is sort of like a scene graph, right? So it's giving you what are the objects and what is their relationship. So when you open up the hierarchy in Unity, you'll see that certain objects have children. And what that relationship, the parent-child relationship, typically means that the parent object is either governing the child in world space, or in the local space, I mean, or it's somehow the child is inheriting characteristics of the parent, right? So just as a programming understanding, that's what that's doing. So I'm going to create a new scene. Now, the first thing we do, Unity provides a default main camera. Just delete that. We provide a prefab in Unity that really encapsulates the device camera. And so this is representing the device camera within the app for you. And it also provides you with the ability to configure the device camera from Unity. And so obviously with AR, we have a consideration where we're providing a calibration profile. Vuforia provides calibration profiles for a lot of devices. And also we end up taking over control of like the field of view of the camera, because it's significant to calibration. And we provide a range of settings in this, which I'm not going to go into until we really need to address them. But for the purpose of developing this app, we provide an AR camera, right? And then we're going to use a cylinder target. Oh, it's not a cylinder target. Provide a cylinder target. And what I'm going to do is come in here and select to load a data set. For the Vuforia platform, all of the targets are recorded in data sets, and they're really the data representation of the target. It's what enables you to track the target. So they represent the target. You bring them into the Unity project, and you load and activate them. And then what we're doing is just selecting to use SodaCan here. This is providing a scale on SodaCan, right? And this is going to give you, what this is giving you is obviously a 3D mesh of the SodaCan, right? Based on the defined dimensions. So to enable Smart Terrain, this is really all you do, is you click the Smart Terrain button, right? And that was in the cylinder target behavior. And you can see now what this is providing you is a primary surface, which is here, and then a prop template, which is just sort of a default template for handling the prop. When I talked about when props are being created, you are taking a template and you're making that concrete by adding a prop instance discovered. So this is just one that's attached by default, just to make it easy for you. So now that I have the Smart Terrain instance in there, and I have my primary surface, what I'm going to do is actually define the world origin to use Smart Terrain. Now the significance of this, what this does, is it makes, within world space, within the Unity context, it makes smart terrain the center of the world. So again, when we're talking about being able to understand where props are, how big props are, where things are situated, using the smart terrain instance as the world center means that in the real world, the correspondence of building out the virtual into the real world, you can then match that accurately into understanding, okay, this virtual object is actually in that position in the real world setting. So that's why we use smart terrain for that role. So what we're going to do here is set that to specific target, which means that I'm actually designating the target and I'm adding smart terrain to that. Now also, I talked about the fact of wanting ground truth reference, right? So when we look at these properties, the side length, and this is all in reference to the cylinder target, these aren't actually accurate for the the unit we use internally is millimeters for smart terrain. So these, this is not a single millimeter high, and it's not 0.6 millimeters across. I have to provide a conversion factor. This is actually 6.6 centimeters. So what I do is go down here and define that I need to convert that. The factor is 100 times the definition of the diameter there. So what that does is it gives me an accurate reference for the true physical dimension of the target. And now that I have that in place, I can go in and start customizing this scene. So one of the first things I'm going to do is just define what I want the primary surface to look like, right? So provided a surface shader here. Now this is really just a standard Unity material, right? Again, there's nothing eccentric about the way that we're handling this. You'll notice over here, this has now been added as a component. We have a wireframe behavior script. You see that green on there? That's really just sort of an indicator to understand mesh updating. I would recommend it for development purposes. You may not want to expose that to the user. It looks a little crazy, so you can turn it off if you choose to. And then what we'll do is, as I mentioned, smart terrain is using an event-driven programming paradigm, meaning that really the significant objects and processes are incorporated in behaviors. What you're doing is registering an event handler with that behavior, and that's how you're receiving callbacks. So we're going to add some custom event handlers to this in order to provide the kind of experience that you'd seen here. So what I do, there's a default event handler. I'm going to turn that off. And then I have some scripts here that we've got. So this one handles really the cylinder. I'm going to add a couple for smart terrain. Again, I'll turn off the default. What the default what the event handlers in for Vuforia, what they're doing is when that object is being detected, it simply looks for all the children and it enables the children. So they appear when that object has been detected. That's really the significance of them. So I'm turning off the default and I'm adding a smart terrain event handler and also the trackable event handler. Now what these are doing, you'll notice here with the smart terrain event handler is this handler actually is what this is doing is handling all the prop associations. You'll notice there's a prop template, and also handling the ice rendering. So let me just go in and add these. So that's the majority of it, and then really all you do past that is add this UI state manager, and what this is doing is controlling the interfaces. When you see, the instructions come up, the screens, that's what's being provided by that. And this needs to know about the penguin. Oh, I forgot to add the penguin. Hold on one second. So here's the penguin. He's the most significant character in here. Right? So add him or her. So you can see it's a standard model. I'm going to drag it in. I'm actually going to turn this off initially so it doesn't appear. You do that up here. I should add a directional light as well just so that you can see everything. Get that out of the way. And then also going to add the iceberg around the cylinder target. And that's really it. So that was, you can do the whole thing, and it's about 15 or 16 steps in going through the entire workflow for creating this. And so the way that what we do within the Unity environment is that we actually do provide a simulation mode, which you can activate here. And what that does is you can use a standard webcam so that you can model this to do rapid prototyping. You don't have to load everything onto a device each time. But this is going to give you really the same experience as what I had shown on the Samsung device. That's about it. Does anybody have any questions?
What is the end-user application of a setup like this?
I think really what we're seeing is we've run a beta on this, and a lot of the interest that we had seen is, again, in creating a game setting, right? So it's people actually creating video games that they can stage in a real-world setting. And it's something that maybe you're playing, like we'll have an ability to show some of these. We had one that was developed by Pateco, who's done Kolar. And what it was essentially an air racing game. You went in, you colored a little airplane, captured that as your target, and then we're able to set up a race course, really using objects like this, that if you've ever seen air races, how they have those pylons in the air and the planes actually fly through them, that's what they were doing, is they were using these as the base, sat out a large race air course or air racing course, and you had the ability to race through that. Other apps that we had seen were people really taking these and making them into game objects within the setting. So there was one that was like a castle attack defense type game. And what these actually then became were towers. One of them, the larger objects became castles. The smaller ones became these sort of pylons that had floating defense towers above them. But that's a lot of what it is. It's, again, the experience is being generated dynamically at runtime. So what it enables you to do in the game development paradigm is to actually enable the user to develop a game level for themselves and start placing physical objects and making them significant to gameplay. That's a lot of it, yeah.
Along those lines with the castle demo, I think I saw a video of online, how do you determine, like, this is a cylinder and so it's going to become a tower? Like, where do you put in that distinction as to what it might turn into?
What you're really looking, because it's not giving you contours, so what you're going to look at is really bounding dimensions for that. So you're not going to know, we're giving you a bounding box, right? So you can apply a cylinder to that, but it's really the shape that's coming through is initially going to be constructed as a cylinder. So really what you're going to look at in understanding how to treat different objects differently is look at their physical dimensions. How tall is it? What is its scale? How wide is it? And that's how you can infer how to treat. Does that make sense? Yeah, how to handle them differently. Oh. Sure. I think that was good. Sure.
When it's scanning the rest of the environment, is it using like a combination of SLAM, or how is it?
It uses a bunch of techniques. It's using, obviously it has a depth sensing capability, but the ability to synthesize edges isn't SLAM, obviously, and the object reconstruction isn't SLAM. So what we've done, and this is really just making it useful to developers, is combined various CV techniques that provide that kind of reconstruction. So it isn't simply, it's not just a raw point cloud. You know what I'm saying? Yeah.
So this isn't in version 2.8.9 of the Unity plugin?
No. It's coming out in 3.0.
Oh, great. Thank you.
Sure.
Hi, I have two questions for you. What's the best platform to develop in? I mean, as far as what's the best computer to buy to be working with these?
As far as running the environment for development?
Yeah.
You know, truthfully, anything, it's not that computationally intensive to just do the authoring workflow. I mean, I don't know, I'm sure someone can recommend one, but any modern computer that isn't being sold as a commodity computer. You know what I'm saying?
Yeah.
I don't have a brand name, but
I'm not really fond of Apples too much.
Yeah, you can definitely you can use a PC with it. I mean, you'll see that you have to figure our SDK is optimized for mobile devices. So as far as running the tracker, any PC is going to overwhelm what you're typically going to get on a mobile device. So the tracker, as far as simulating the scene, is very, very efficient. You know what I'm saying? Yeah.
The other thing is, you were talking about the children. When you turn the thing on, it recognizes children. If you haven't created anything for those children,
oh, you mean within the scene?
At what point do you create the children, before or after?
So, you know what there's different ways of handling it. You can do it programmatically, meaning that you can just take the references returned and hold on to them and then do something with them at a certain point. But really, the easiest way of handling it is as an authoring workflow, meaning that go ahead and predefine the children. You don't have to enable them initially. If you choose to have them do something later and you don't want it to happen immediately, you can go through, and Unity's very good about enabling you to sort of go in, isolate a certain object, enable and disable it, and as far as the API to do that is pretty basic. So does that answer your question?
Yeah, I mean, like, is there a timing? You know how layers do things? Would it be done in layers, or would it be done because of a certain action?
It would be. I think it would be done because of an event. Yeah, I mean, it's not. We don't have like the notion of sort of stacking layers of events. What you would do with our SDK is really handling it as like a simple event handling paradigm. It's kind of like web programming or programming in Flash. Is you're going to wait for something to happen, and then when that callback is made, you can go ahead and customize what you want to do.
Yes, hello. One more question, please. So this technology is basically a substitute for infrared scanning, which is used in Kinect, for example, for the scanning of the environment. Do you still see the need to integrate infrared scanning in mobile devices, or
what we're going to do,
completely substitute
if you guys are familiar with the platform, we've previously demonstrated similar techniques using the Capri sensor, which is a structured light IR sensor. So really the role of Vuforia going forward with this range of depth sensing technologies is that we're going to support all of them that are viable, really. And whatever architectural reference comes out for that, whatever type of hardware, we can abstract that and provide a useful API that enables you to sort of write once and run anywhere across the range of depth sensing devices. We like demonstrating this because it's viable for today's devices. It runs on any smartphone that's a multi-core smartphone that we support for Android or iOS. And then as we move forward and we're looking at IR, structured light, time of flight stuff, stereo camera, whatever it may be, we can abstract those as well and provide this and even more advanced capabilities as we go forward.